Hello, welcome to LeetCode Solver. Today we are going to solve sixth problem in May LeetCoding challenge, and the problem name is majority element. Well, given an array of size n, find the majority element. The majority element is the element that appears more than n by 2 times, floor of n by 2 times. You may assume that the array is non-empty and majority element always exists. Nice. In the array. Well, so 3, 2, 3 out of 3, 3 by 2 plus 3 by 2 is 1. So the element should occur more than once. That means at least 2 times. So 3 occurs here at least 2 times. So 3 is answer. And 1, 2, 3, 4, 5, 6, 7. 7 divided by 2 as a floor will be 3. Well, element should occur at least element should occur more than 3, so which is at least 4, and here we can see 2 occurs exactly 4 times, so 2 is the answer. Well, so the brute force approach, if we think about this, then the brute force approach will be just iterating over nums 2 times, like one times fixing the current element and another times another loop for just iterating over whole element and seeing whether the element at ith position is equals to element at jth position. So if they are same, then we will calculate the count for each element. So in this way we can find the count for each element, and then after we will maximize the counter. So and the maximum counter is the answer. Well, because there always exists answer which have more than n by 2 elements. So yeah, in this way we can solve it, but complexity would be big of any square, or any the size of the given array. In this case we don't have to use any extra memory, so space complexity is constant. Well, this is the brute force approach, and another elegant approach will be just instead of just iterating 2 times, we can just store the elements in nums elements in some kind of lookup tables having each frequency, like the lookup table will contain each x will pair with how many times it occurs. So there will be occurrence, number of times occurrence of element, and while doing this, like just iterating over the nums, we can maintain this hash map which contains for each element it contains number of occurrence, and in some point of time we find out that the number of occurrence is greater than n by 2, where n is the length of the given nums. So if we found something like this, then we will just return. Well, this is a solution which have a complexity of big of n for both space and time complexity. So yeah, we can go for this solution. Well, let me define a hash map which map each number with its frequency, number of occurrence. So say occurrences sounds good name. Let's iterate over each element in the given array, and let's update the occurrences of each element will be increased every time, and in some point of time if we found that occurrences of x is greater than n by 2, well, in that case we can simply return x. Well, let's define n as well. N is the size of given array. Well, as the answer exists, we don't have to return anything after this, but we can simply return something so that the compiler will not complain. Let's try with the test case like 333, answer should be 3. As the answer always exists, so we can't write any invalid case like 321 is invalid case. Instead we can write 322, answer should be 2. Yeah, let's write case like 3 3 4 elements where 3 is the majority. We can submit. Well, accepted. Nice. So can we do better? Well, what we can do is, as we are using extra memory, we can somehow optimize extra memory or what? Well, so we can optimize extra memory by, instead of holding this occurrence, what we can do is we can simply, as the number of elements, as one of the element will be greater than n by 2. So if we simply sort the element, then what will be like, if the given array is like 3 2 3 3 as we had in example, then after sorting it will be 2 3 3 3 majority element. Let's, there are 3 element like 3 2 3, and after sorting it will be 2 3 3. Well, this is also after sorting. Well, what we can see is that the element which is major is always be there in its n by 2 index. Well, if it is 4 length, then in 2 0 1 2, well, in this position the element will occur. Even if like there was 2 majority, like instead of, if we toggle in between 2 and 3 so that 2 will occur earlier, then we also see that 2 will be here like in 4 by 2 element. That is why it is measure 4 by 2. So 2 0 1 2, here we can see 2, which is more than half. And in case of odd length element, we can also observe that like 3 by 2 is 1. So first index, let's see in the first index 0 1. So this is the middle, exactly middle in the odd length array. We have like majority elements will occur in exactly middle position. That's why it's middle. That's why it is majority element. So if we have a toggle in between 2 and 3, something like this, even in this case we can see that majority element occurs in the middle position. So instead of doing this, we can simply sort the element nums dot begin, and we'll just simply return nums at n by 2 position. Well, this solution also accepted. The solution is like we optimize the space complexity for sure, because we are not using any extra memory, we are just defining in. Well, we can but however we increase the time complexity by log n times. So sorting will take us n log n time complexity. If we are sure about the type of element, what will be the type, then like what is the major maximum range or minimum range, then we could have done counting sort, which will, like, if the element occurs in 1 to n range, then which will have complexity of big of n. So overall time complexity would be big of n, and issues complexity would be a constant in that case. But generally, if we do sorting, then the efficient sorting algorithm will provide us n log n solution complexity. So this is not this is not a perfect solution. So we reduces our space complexity, however we increase our time complexity. So let's go for the solution, which will have, like, this solution we can note down. This solution has big of n log n time complexity, however big of constant space complexity. That's really nice. This is in case of space complexity we are good, but time complexity we can still think about it. So if we have to do this, then there exists a well-known algorithm which is called Boer-Moore algorithm, voting algorithm, yes, which will basically useful for finding the majority vote. Well, this is how it was invented, this algorithm. So what does it do? Basically, it will it is based on the fact that like, if we go through the given numbers in the given format, like whatever it is, either sorted or unsorted, then we always know the fact that majority element can always cancel out all other elements and still survive. Like, if we partition the given array somehow with the non-minority element, non-majority in one side, and there is a race or fighting in between non-majority and majority element, say, we can think about something like that. There is a fighting in between these non-majority elements and majority elements, and in fighting, like, there are kind of x number of non-majority element, and there are y number of majority element, and we know that y is always greater than x, and all y are same, and all non-majority elements may be same or may not be same. Well, so if we cancel out, if we find out any majority element, we will increase our counter by 1, and in the case we found non-majority elements, we will decrease our counter. So eventually, in the beginning, we don't know which one is majority or non-majority, so there is no any way of determining. So even if we start with a non-majority element, considering it as a majority element, then uh, if we get some value, then we'll increase our counter, and if we get here majority element, we'll decrease our counter. Well, by doing so, in some point of time, we see that uh, we may go, like, to the zero, because every non-majority elements will not survive if we have majority elements which is cancelling their counter. If they are uh, if they are being considered as a majority and being uh, increase their counting. So this is I mean worst case scenario where we are assuming that non-majority elements is a majority element and increasing our counter. In the meanwhile, majority elements will, when they they are in place, they when we encounter majority elements, we are decreasing their counter. So at some point of time, while going through left to right, we are in a situation that we erase some non-majority elements and we erase some majority elements, and we notice that if we erase x or a amount of majority element, then we deleted exactly a amount of minority element. So a1, if so the majority element we deleted a amount of, but there could be some cases like if I found non-majority elements like this, the is going from left to right, I was encountering say 5 and 7 and 8 and 9. So I consider 5 as a majority and I go here and I decreases their counter. So 5 is no more major. So maybe let's assume majority element is 9, and initially I fired both of them. So actually I'm decreasing my majority counter. So non-majority, I am removing my non-majority elements. So my majority is not being affected. So I remove both of them without affecting our majority elements in the future. So when we come to 8, we assume that this is a majority, and when we come to 9, we decreases the majority counter as well. Now every majority counter is now 0, and we will have a fresh start from this position to the end. So for that suffix we will do the same thing. Well, we are doing the same thing for the suffix, and whatever happened before is not affecting majority elements, because the number of majority elements deleted will be at most a amount, and the in the same case, like when a amount of majority elements deleted, a majority elements removed. If a amount of majority element removed, then at most or at least a amount of, exactly at least, because some non-majority elements are being killed by non-majority elements. So at at most, no, at least a amount, at least, because we deleted here, we have case of 5, 7, 8, 9, and 9 was the majority one. We deleted only one 9. However, we deleted 3 non-majority elements. So at least a amount of non-majority element deleted. Then we will have to solve, then everything is settled down, then we have to solve suffix starting from say ith position till the end. So definitely in this range, definitely in range I to end, that majority element will be majority element for sure, because whatever deleted before, say k numbers deleted, then at most k by 2 majority element deleted. So that is why we are not deleting. Well, that is why we are not deleting prefix having more majority element. So that is why we can have a fresh start from. So we can easily have fresh start for range I to int. This is the logic of Boer-Moore voting algorithm. Well, let's go for the implementation. Implementation is similar, like we have to maintain the counter. So say majority counter is 0 initially, and say majority element is not defined, so let's say -1 majority counter. So whenever we have majority counter 0, then we will assign that majority element. Well, let's iterate over given norms, and if we see that majority or counter is 0, while if we see majority count is 0, then we have to have majority element updated. Majority element will be equal to x, and our majority counter will be equal to 1 as well in the case of majority counter 0. Else, if the majority counter is not 0, then if our current element is equals to majority element, then we will definitely increase our majority counter. Else, what we will do, we will just reduce majority counter. Majority counter decrease. Well, now finally we will return our majority element. Well, since the answer exists, we don't need to verify again, like iterating and taking count of how many times this majority element occurs. Well, x and 1, x is majority element, then increase counter, otherwise decrease counter. Sounds good to me. So let's see what happens, how it works for this case. Shorter case, 3 to 1. Initially this is 0, this is -1, and when it goes here we see that this is 0, so we update our majority element as 3, and we increase our majority count as 1. And when we know else condition, next time we reach here and 2 is there, and we see that majority counter is not 0, so we go here and we try to compare 2 with the majority element, but majority element has already been settled to 3, so we decrease our majority counter. So majority counter becomes 0, and we are ignoring as a whole this. And now we have a fresh start. So in a fresh start, we go again here in this position, tooth position, and we see that our majority count is 0. So we are again settling our majority element is current element, which is 3, and our counter is increased to 1. So finally we are getting major element. Well, in this way the algorithm works. Time complexity and is big of n for sure, because we are looping over whole elements, and space complexity is constant because we are not using any extra space. So that is why the time is big of n, where n is the size of the array, and space is constant, which we can also say big of 1. Well, let's run the code and see if there is any comparison error or not. Well, as expected, comparison error, majority element 35. Spelling mistake, element, okay, and 29, majority, okay. If I fix that, then it should fix everything. Sounds good. Let's submit and see. Accepted. Awesome. So this is also called Bohr voting algorithm. Yes. Thank you so much for watching this video. Hope you like it, and if you are looking for similar video, feel free to subscribe the channel. And if you have any alternate solution or any ideas, anything you want to share, please feel free to comment in comment section of the video. Okay, all right. Have a nice day.